1.3 billion light-years away, there existed a pair of black holes in a binary system, one 29 solar masses and the other 36 solar masses. As billions of years passed, these spectacular black holes begin to lose energy, causing them to spiral inwards faster and faster, and finally merging with a cataclysmic collision to produce a single massive black hole. At the final second of the collision, these black holes can reach immense speeds, up to half the speed of light. Fascinating, but let me tell you what's even more fascinating. Recall this, our initial black holes were 36 and 29 solar masses, which would add up to a total of 65 solar masses. However, scientists measured the resulting black hole to be only 62 solar masses. This black hole appears to be missing a whopping 3 solar masses. It turns out that according to Einstein's famous E equals to mc squared, the missing 3 solar masses were converted into energy which was released in the form of the mysterious gravitational waves. These gravitational waves ripple through the universe, causing distortions through time and space. The energy dissipates, and by the time the waves reach Earth, they become incredibly weak, making it extremely difficult for scientists on Earth to detect them. Now back to the black hole 1.3 billion years away. This violent collision generated the first gravitational waves ever detected by mankind on 14 September 2015 at 5:51 am. These waves were detected in the USA by two megastructures. The first signal was detected in Livingston. A mere 7 milliseconds later, a second signal was detected in Hanford. These megastructures are called LIGO, which stands for Laser Interferometer Gravitational Waves Observatory, and each LIGO has two long arms spanning 4 km long. Having said this, what exactly is a gravitational interferometer and how does it work? Just like a satellite dish, a gravitational interferometer picks up waves, but instead of radio waves, it picks up gravitational waves. To explain how LIGO works, we have to first know its components: a light source, a beam splitter, mirrors, and a photodetector. And here's a simple LIGO. In this setup, light will be emitted from a laser, which is split by the beam splitter and directed towards two mirrors. If the length of the arms are exactly the same without any distortion in space, the reflected waves will come into contact with one another and recombine as a normal phase wave before it reaches the photodetector. The whole process returns as a normal light wave. However, as gravitational waves hit Earth, time and space is distorted and the length of the LIGO arms changes. As gravitational waves pass through the megastructure, it changes the length of LIGO's arms. This results in an antiphase recombinant wave. The photodetector will then detect a different wave from the initial output, allowing us to measure gravitational waves directly. So how confident is LIGO in detecting gravitational waves? A whopping 99.9994%! Upon the recent confirmation of gravitational waves, headlines begin flooding the newspapers. 100 years of gravitational waves. Who discovered gravitational waves and where did they come from? In 1916, Albert Einstein predicted the existence of gravitational waves in his general theory of relativity, which stated that massive accelerating objects orbiting each other will travel at the speed of light through the universe, carrying clues to the nature of gravity and their cataclysmic origins. 20 years after Einstein's death, two astronomers at Arecibo Radio Observatory in Puerto Rico discovered a binary pulsar, two extremely dense and heavy stars in orbit around each other, and proved the general theory of relativity. The 40-year monitoring of their change in orbit proved this theory. However, such proofs were only indirectly or mathematically. Finally, in 2016, scientists announced the detection and confirmation of gravitational waves that Einstein predicted a century ago. But what's so significant about gravitational waves anyway? For one, it gives us a deeper understanding on cataclysmic events and the early universe, because such events in the distant universe emit more gravitational waves than electromagnetic waves. This gives us insights into space and time. Scientists have also speculated that spacecraft could ride on gravitational waves, reducing the need for fuel and increasing the cost-effectiveness of space flights. Gravitational waves bring unlimited possibilities like harnessing energy for household users. These can only be discovered upon further understanding and research. As we usher in new studies in physics, astronomy, and astrophysics, let's stay tuned to what gravitational waves continue to bring. Let us ride the waves towards the future of science and astronomy.